So we had a few questions about class imbalance and sampling. As an overview, we do have a heavy class imbalance with it being skewed towards 5-star ratings. And we also have a token length imbalance, so our 5-star reviews tend to be extremely short. For both latent Dirichlet allocation and non-negative matrix factorization, these are heavily affected by the length of the documents. So what we ended up doing is separating these into negative, neutral, and positive reviews. Then we used undersampling that gave a higher probability of selecting longer reviews. We had a couple of questions about this that we wanted to address. First of all, we did not want to choose only the extremes, and that's for several reasons. We had a few people that suggested we look at just 1 or 5-star reviews. But first of all, our ultimate goal is a little bit more nuanced than just positive or negative sentiment. First of all, we do want to understand what kind of topics, what are the users saying about these apps, what is in the reviews, not just positive or negative sentiment. And also, if we do want to make predictions, we're looking at really a 5-star scale where there is a difference between a 2 and a 3-star review. Secondly, our data set isn't very large, so we really want to drop as little data as possible. And if we're looking just at 1 and 5-star reviews, we're going to end up dropping more data than we need to. And finally, we are a little bit worried about fake reviews or the possible presence of fake reviews, which we assume would probably cluster at the polls. Since we don't have any kind of ground truth for fake or not fake in this data set, it's hard for us to really do much about that. But we are worried about over-relying on those two reviews. So as an example of how we're moving forward, one thing we're looking at for LDA and NMF is topic coherence to measure performance. So the best measure of whether LDA is performing well is really whether or not the topics are semantically similar. In other words, are they human understandable? So to do so, we're going to use the UMass metric, and you can find out more about that in this article. The UMass metric, though, is really a variation of pointwise mutual information. So we're computing document co-occurrence of words in the topics from the original corpus. And there's the formula there. We're going to use this metric for hyperparameter tuning, and we hope to look at number of topics, methods of text cleaning, and also n-gram length. The problem that we're running into right now is that this is very calculation intensive. Even running on 16-core Amazon EC2 instance with asynchronous parallelization, it's still taking 36 hours to calculate the UMass metric for all 5 of our cross-fold validations for each hyperparameter. So it's a time-consuming process, and it's not one that we can very easily build on iteratively since it takes so long. This is also only using the top 10 n-grams in each topic, and the way that the formula works, it would scale exponentially, so it's very difficult to go past this given our current computing power.
Hello everyone, my name is Shreshtha and this is the Milestone 4 presentation for my work on word embeddings as part of the NLP group. I have experimented with word2vec for the most part of last few weeks, and I have created a lot of models. They are divided into 2 main categories: contiguous bag of words and skipgram. I found that CBOW works better than skipgram. Within CBOW, I have tried a lot of hyperparameter tuning. Like I've tried different vector sizes, 100, 150, 250, different learning rates. I have tried bigram and trigram transformations. I have tried stemming and lemmatization. I have also tried variations with the negative sampling values and window size. So on the right, what you see is a plot of training loss versus of the epochs in various models. So the first graph shows you the variation of model training loss when the size parameter was varied. So we see that size 250 gives us the lowest training loss. Similarly, the second graph shows the training loss variation with the alpha values, and the third one shows the training loss variation with the various CBAO model with and without stemming, and the skip-gram model with and without stemming. So we see that the best model on the training comes out to be the word-to-vec model with a vector size of 250, a CBAO algorithm, window size of 2, and a negative sampling of 2. However, I have for the sake of evaluating the accuracies, I have compared it with a skip-gram model of similar parameters, and I have measured the accuracies on 3 levels. So there was a question answers list that was published with Word2Vec, published by Google when they published Word2Vec, and it contains a lot of questions and answers in the form like what A is to B is what C is to D. So they have countries and capitals, they have comparative grams, they have plurals, they have verbs and adverbs, and those things, and in the end they publish a total accuracy over the complete set of question and answers. The second measure that I have taken for evaluating is that Word2Vec provides a function, predict output word, which takes in a bunch of context words and try to predict the pivot word. So that's what I have done. I have divided the corpus into test and train, and then after I train my model, I predict my test sentences using the same rolling window that was used at the time of training, and then I count how many pivot words were correctly predicted. However, I ignored the pivot words that are not correctly predicted, and I calculate the accuracy as total predicted divided by total number of words in the sentence, and then I take a mean over this accuracy for the whole test corpus. And the third is that I measure the corpus perplexity as spitted out by the model. So what I do is this predict output word gives you the probability of predicting the pivot word, and so I use that probability to calculate the probability of a sentence, and then from that sentence I calculate the perplexity of the corpus. The formula is shown in the slide, and on the right you see the comparative values for both the models, skipgram and CBAO. So we see that both the models perform similarly on the Google question answers, but however on the other two measures of accuracy, CBAO is performing marginally better. To visualize more of the performance, I then do some similarity checks. So we see that here there are 3 random words that I've checked, like navigation, Google Maps, and bad. And although we see that the words that it has rendered as similar are actually relevant words, but the similarity values are pretty low. This kind of suggests that the data is not sufficient enough to learn the syntactical or contextual similarities between the words. The next thing that I do is try to cluster these words together to see if I can derive some topics. So this is just a bar graph showing the distribution of words into different clusters, and we see that the greatest cluster has about 1,000 words clustered in it, and the cluster distribution is not uniform. It doesn't show any pattern as such. And this is a graph where it shows the top 10 words of each cluster, and these are 5 randomly selected clusters. So we see that the yellow cluster and the green cluster looks a little bit well built in terms of the words that it has taken into account, and the words look quite close to each other. However, the rest of the 3 clusters are not so well formed, and there is quite a bit of overlap between them. So this again reiterates uh, the drawback that we have been feeling, that this data set is not enough, and the sentences are not well formed enough to learn the syntactical similarities between the words. The I experiment is doc2vec. So doc2vec is an improvement over word2vec in the sense that in addition to the word vector, we also have a vector which represents the complete document or the complete paragraph, depending on how you divide your text corpus. So this model, I have not experimented much with the hyperparameters. I've created only a couple of models, one of which is with vector size 100 and a negative sampling of 5 and a window of 2. So this has shown good similarities between documents, although not such a great cluster representation. So on the right you see the most similar documents to the one that is mentioned in the to the sentence that is mentioned in the square brackets. So you see that not only the sentences are relevant, their similarities are also quite good. And when we rank this particular sentence similarity with itself, it comes out to be 0. So this is kind of a sanity check on the model to see that our model is not going haywire. You can see in the second example it behaves the same way. And however, when I try to cluster this, I created about 50 clusters using k-means, and if we see these are the words that I'm showing for 4 random clusters, and we see that although it does seem one of the cluster does seem to present a theme or a topic, they are not well formed enough to give you a clear topic representation. So the future work would be of exploring more with doc2vec and finding a metric to measure the hyperparameter tuning effect. If I can find something for perplexity calculations for the topics that I discover by clustering, effect of bigrams or diagrams, I can experiment with the clustering itself. And this is where I think I do not remember, but somebody had pointed out about the elbow method for clustering. They had also forwarded the link for that, and I think that would come useful here. We are also thinking of using these doc2vec vectors to train a classifier, but that is something that would be the purview of other member of my team, but we will have more on that maybe in the final presentation. Thank you.